Hi everyone, welcome to the second session of the 5G Massive MIMO training. In the previous session, we covered a very important concepts about the antenna solution in general, and also we recap some of the knowledge about the MIMO, which is a traditional MIMO. And all these points is very, very important because if you really understand, you will understand what it means by massive MIMO, why we need massive MIMO, and so on. So the first part we covered last time, it was about the passive antenna, which is being used by traditional MIMO or the 4G in general, and the active antenna, which is a massive antenna. And we highlighted that the massive antenna or massive MIMO is having up to 128 or 64 antenna, TXRX, and can including even 128 or even 256 antenna elements, and we explain what is the importance of these antenna elements and so on. So in today's session, we are going to cover these parts, which is first, what is the massive MIMO, and why do we need massive MIMO? What kind of benefits we can get? Then we will go through a very basic understanding about how the data, in general, data stream in the physical layer is being processed. Because this one I will try to address, or will take a high level for it, because I need to address which points in the physical layer processing where the radio optimization can do some tuning to improve the massive MIMO performance in general. Then we go through some important concepts about the single user MIMO and multi-user MIMO and the differences between the channel reciprocity and codebook in a high-level view before we jump next session into the very deep details, which will really cover a lot of complex information and in a simple way, or I will try to make it in a very easy way. So let's move forward and see what we have. So the first part we have here, it is what is a massive MIMO. This one was kind of covered in the previous session. Again, as we highlighted before, the massive MIMO, the legacy MIMO or the traditional MIMO is using this kind of passive antenna, which is, as you can see here, it's having a small number of transmission and receiver. For example, maximum 8 transmitter and 8 receiver, or usually it was 4 and 4 or 2 and 2, as you can see, and it's a few number of antenna elements. So this one was resulting of having a wide beam, as you can see here, and the beam was being fixed and shaped to transmit in a particular direction. And while in the massive MIMO, we can have now much more antenna, transmission antenna up to 64, even higher in the, if you're speaking about the milliwave, and you have a lot of antenna elements, which was this small size within the antenna. I already presented that in the previous session and showing how even the actual antenna looks like. And this was helping in generating narrower beams and improving your beamforming in general, which is being reflected in your CNR quality and can have an improvement, additional improvement in terms of throughput and single user MIMO or multi-user MIMO. And also the other benefits we have highlighted, that in the legacy antenna, we used to have only 1D coverage, like for example, only covering the horizontal plane. But now in the massive MIMO, because we have this kind of more antenna elements, again, I'm stressing to antenna elements because it's the most important. You can have this more vertical planes and horizontal planes. So now you can even cover and move your direction. As you can see, you can cover part of the sub-array or antenna array to cover the vertical plane, and the other is to cover, for example, the horizontal plane. So now we have a 2D active antenna system where it's can cover both vertical and horizontal. This is what is massive MIMO as a high level can do, that it can have much better beamforming and number of beams, and can also cover the vertical and horizontal. And for sure, this will be covered in much more detail in the next slides. Let's move forward. So now, usually the question which was being asked during the initial deployment of the 5G, or even when you introduce a massive MIMO to 4G and so on, why do you need massive MIMO, or why massive MIMO in general? In a simple way, massive MIMO is the enabler for the 5G. Without the massive MIMO, you will not have a real 5G network. For example, as you know that the 5G in general require, especially the advanced phase, which is, I believe, not all networks is focusing in this part, but it's mainly like trying to provide additional service like enhanced MBB, like mobile broadband, and URLC, which is ultra low latency, and the massive machine type, and so on. This is all required a massive antenna or a massive MIMO. Why? Because many of those will require a much better coverage and a much better capacity. Even if you're speaking about the milliwave, this is like having a high capacity. So the high capacity will have a higher penetration loss and more losses. So you require something to improve your coverage and capacity. And this is one of the benefits which is being by the massive MIMO. In addition to this, that usually now the most of the focus, for sure, it's AEMBB. The later the other service will come into the figure in much more larger scale. That the MBB is not just about to serve faster transmission speeds when a user is near to the, for example, unit B or the tiers, but it also needed to deliver unparalleled and end user experience in crowd areas, which is I can summarize in the word of multi-user MIMO. As mentioned here, for example, massive MIMO refers to an antenna array employing a large number of antenna elements to serve multiple users simultaneously, which is again about the multi-user MIMO. So again, now what is the benefits of massive MIMO? We know that we need massive MIMO because it's key enablers of the 5G in general. So what kind of benefits massive MIMO can provide in 5G? The first part, as you can see here, it's about the capacity point of view. If you zoom in here, capacity, because this one will take us into serving multiple users through allocating different beams, as you can see here. So all of them, this is a multi-user MIMO, all of them can being allocated the full resource blocks. For example, if you have 273, so each one of those can take the full use of the full frequencies as long as they are allocated geographically in the different location or in different space domain and so on. So this is the first part. It will increase your capacity even without extending your bandwidth. Assuming that you have a limited bandwidth 100 megahertz, so massive MIMO can even give you extra gain up to 5 times and even more because of this kind of function of multi-user MIMO, because it can allocate different beams to different users. And those beams means that each user will reuse the full resource box, but in a space domain or in a different layer, so they will not be interfering each other. This is the first part. The second one, which is very, very important, particularly for the 5G and for the high band in general, it's about the coverage point of view. As you highlighted before, the 4G having a wide beam, okay, and as you can see, for example, the wide beam was not concentrating, or the antenna gain was much less because it's like the energy is being divided along the wide beam here. However, in the massive MIMO now we have more sharp beams or more narrower beams, and this beams, like in general, it's different. We have different for broadcast, for shared channel, and so on. This is all will be covered in details as well in the future, in the next sessions. But just to understand now, the coverage mainly coming from you have more antenna elements, which can help you to generate more narrower beams, which can even reach edge users in more concentrated energy here, as you can see here. And in the same time, it's reducing the interference between the users because each one of those is allocating a different beam with some separation between both of them. So this is also can improve your not only signal strength, but also the quality or the CNR. And the most important point, it's about milliwave enablement in general. Without milliwave, without massive MIMO, milliwave will not function that much because, as you know, milliwave have a very high band and it's having a very limited coverage. So you need all the advantage mentioned, especially for the coverage part, to improve the coverage of the milliwave. And milliwave, it will be up to requiring having a high bandwidth, for example, up for 400 megahertz. But in case if you don't have coverage, this will be useless. So that's why it's require a massive MIMO. Then the part which was already highlighted, it's about the 3D or 2D beamforming, where we can cover the elevation and both horizontal plane. So this is the main advantage of massive MIMO, and all of that was being achieved, as we explained in the previous session, that we have diversity gain, we have array gain, we have the beamforming gain. All of that was already presented in the MIMO, but now it's become even much more efficient and much better gain for in terms of massive MIMO because of the higher antenna elements and so on. And also there is something called interference suppression gain. I'll just give a quick introduction, or even try to reduce the interference in general, especially in the out of the main beam. If you remember in the previous session, we highlighted something about the antenna specification, something about the beam loops and side loops and even the back loop and so on. And this is actually where the also more antenna elements can help into generating something called constructive and destructive interference. Let me give you a quick introduction about both of them. I believe you're already aware, but just to create the theoretical information. As you can see here, this is assuming this is a single antenna. For example, it doesn't have many antenna elements, and here, for example, it's increased by 2. As an example, you can see initially the beam was like a wide beam here, but now once you have 2 antenna elements, now the main beam become more narrower and even more stronger. As you can see, more concentrated and more focused. And even the side beams now, you can see here, become having a null. So this is like not causing interference. Even those one become less compared to the previous situations. This has become weaker. How this can be done? This can be done through that something called interference, like the constructive interference. For example, as you can see here, as you remember, we mentioned that we have this dipole plus 45 minus 45 and so on. So what it will try to do here, the antenna, it will just generate from the 2 antennas or the 2 antenna elements or whatever you have here, it will generate signal with the same phase. As you can see here, both of them, signal 1 and signal 2, both having the same phase. So this one will be accumulated together, it will be added together, so it will result into a higher gain, as you can see here, which is called constructive gain, because both of them have the same phase, so it will add additional gain. While the the destructive interference, which is mainly to improve the side loop, and again, if you remember, we called the side loop or the back loop last time as unwanted signal, because this usually cause interference for the other user. For example, served by other region would be in this direction. So what this do, as you can see, it just generate waves in opposite phase through canceling each other. How do that? You can see this one, for example, generated like this one generated like this, and at the end it will result into canceling each other. So this will result in much less interference. And there is a very good video about that one explaining. I already quoted this picture from this video. It's in YouTube. I will add the video also in the video description, which is also covering about the antenna array, and also it's having a lot of good information about the antenna in general. You can refer to this channel. So let me get back to the previous slide. So this was overall about the why Massive MIMO and what is kind of benefits we can get from Massive MIMO and this kind of high level. So now I will jump into the features and the data stream and see what we can get from this the next session, for the next slides. So before going to the features of Massive MIMO, which is single user MIMO and multi-user MIMO, and differences between channel reciprocity and codebook and so on, I would like you first to take you through this data stream physical layer processing. And the main reason it's kind of looks complicated, but the main reason for that, I would like just to address the some important points that from where or how, which kind of those data stream, a part of this data stream can be optimized, or usually we as optimization engineer, we try to look into and try to do some tuning. So let me explain this figure here about the physical layer processing in general. And even if you need more details, you can find it in the 5G NR in bullets and also in the next generation book as well. So let me explain what it means by all of that and what kind of points we need to focus whenever we doing our optimization. So how the data in general is being processed at the physical layer. As you can see in the figure in the right here, initially there is something called a transport block. This transport block here, as you can see, is our bucket, the data actually, which is being passed between the MAC layer to the physical layer, and it's passed it's passed downwards at the transmission. For example, we are assuming this is a downlink, so it's passed in the downlink direction from the MAC to the physical and processing through the physical layer. This is whenever you're talking about the transmission or the TX, and upwards at the receiver. For example, if you're speaking after the data is being received to the user, so it will pass first from the physical layer, then it will go through upwards to the MAC layer and so on. So in general, again, the data starts first as a transport block in the MAC layer, then which is likely being a big package of information. Then it's going through some error detection and correction. For example, initially, as you can see, there is something called CRC attachment. But before doing it through the cycling advice check, I would like to highlight that usually the transport block in general can be 1 or 2 transport block for each location. For example, in downlink, there is a maximum 8 layers, can be generated for MIMO. So one transport block, it's equivalent to one code word. We'll speak about the code word later. And one transport block requires up to 4 layers, and two transport blocks require 4 up to 8 layers. And we'll be speaking about this kind of details in general. So again, our transport block or data starts as something called transport block on the MAC layer, then it's for the physical layer. Then once the transport block passed here, it will initially having something called cycling redundancy check or CRC, which is additional bits will be added to the transport block, and this will be allocated in general to provide an error detection capability at the UE. And this is error detection capability, not error correction. The UE just can, through this additional bits, which is called cycle redundancy check, the UE can detect the error. And in case if he detected there is an error, he will report, like for example, a non-acknowledgement means that there is an error. I would like to have a retransmission. So as you can see in the figure in the bottom left here, there was a transport block initially, and there is a CRC being attached with cycle redundancy check. And this size can be actually varying, even it becomes 16 bits or 24 bits. And this is one of the additional or advanced things done on top of the 4G network. For example, the 4G was being fixed to 24 bits all the time, despite what is the size of the transport block size. But now in the 5G, it can reduce the bits, which is at the end, we can consider as overhead, from 24 to 16 in case of the transport block size is less than a specific value, which is 3824 bits. So the transport block is less than 3824, it will assign 16 bits in general. So this is the first part here about the CRC attachment or CRC addition to the transport block. Actually, the next part, by the way, this is all like a theoretical information. You can even skip, especially for the part on the left. When I go to the part right, this will be more important. But this is kind of theoretical information. You can even skip to the next part of this video in case, like, if can be considered as additional, you will not really need it in your daily optimization. So you just to understand. So after the CRC being added to the transport block, this all will go through something called LDBC. And this is, if you remember, it's called low density parity check. And this is actually also something advanced or additional. It was not being used before in the 4G. 4G before was using alternative solution called the turbo coding, right? And it was being used in turbo coding in 4G or BDSCH in 4G in general, and it was used also for HSDB in 3G. However, the LDBC provide a better performance, especially in terms of reducing the complexity for both the encoding and decoding at the receiver side. And this can result in a lower power consumption in general. And this is actually in general, it's necessary prior to the channel coding in general. And this is why, because it determines the maximum. If you look into this figure in the bottom left here, it just determines the maximum code block size and impacts that requirements for the segmentation. For example, it just requires what is the maximum transport block size and what is the equivalent coding rate. And based on this data information, it will decide whether this one required a block segmentation or not. For example, if the transport block is very big, so to require an additional segmentation, as you can see here, and the segmentation actually in general just being required to ensure that the maximum code block size is not exceeded, because if the case of exceeded, it will cause problems whenever you are going to transmit in the air interface. Then you just go through, after the channel coding, go through something called the rate matching, which is actually, it's just like an extra step on top of the channel coding. Just it's required. It's just ensured to reduce the number of bits of channel coded bits in case if it's very high, to match the air interface capability. This one having the information about the air interface capability, so it will just try to reduce the channel coded bits in case of that. Then after that, all of that, whatever being segmented here, if you have a segmentation, there will be a code block concatenation, then it will be forwarded here to the as a code word, and then it will starting something called the scrambling. And in general, the objective of the scrambling is to randomize the bit sequence, and this is for sure will like a kind of interference improvement, like randomizing the interference in general generated by the BDSH if you randomize the bits in general. Then now moving forward to the very important parts, which is the next three parts, which is about the modulation. And this is for sure just try to map whatever bits you have into a modulation symbols. For example, as you know, QBSK 64, 16 QAM, 64 QAM, 256 QAM. And this is actually part of the link adaptation, right? So in the GNB, usually have a lot of parameters which can play around with a sign modulation scheme. So here, this is the most important in terms of optimization. Usually we play around with that a lot. There's a lot of actions. We can mention some of them later on. Then once we assign the bits into duration symbols, after that it will go through something called layer mapping, and this is in general used to map those modulation symbols into a number of specific layers. For example, if you're speaking about the single user MIMO, you have up to maximum eight layers, right? Or eight, like we can say rank 8 or rank 4, which is eight different data streams. And at the end, this is for single user MIMO. This is also, you can configure it. You can limit the number of layers. But first of all, you need to understand that the maximum number of layers is determined by the maximum number of transmission, the minimum, this formula, which is a minimum Tx under X, which means, for example, if you have 4 transmitter or 64 transmitter, let's say 64 Tx in the, for example, unit B side, but however, you have only 8 in the UE side, then it will take the minimum of both of them. So this means I have only maximum 8 layers can be transmitted. And also, if, for example, we have only two RX from the receiver side, which is IUE, this means the maximum layers can be only up to 8. But again, here, this is layer mapping. This is one of the things also we can play around. For example, if you're speaking about the multi-user MIMO, if you are speaking about 64 anthem, you can have up to 16 layers. So this is also you can play around. For example, in case if you having only 4 or have only 4 being there or 8, so this means you are limiting the bearing performance or multi-user performance. So you can play around with the current configuration, but at the end, this is depend on the hardware or the product or even the software of your vendor, in case if you would like to tune this kind of layer mapping. But just important point to understand about layer mapping in general, that in general, the GNB will consider that it should match the current channel condition between the TX and RX whenever it's trying to transmit or send the number or different number of layers. And also one of the things that sometimes this is, or like it's not necessary actually to allocate high number of users or high number of layers, sorry, if the UE, for example, if the user is having a low traffic volume. And this is also, I think, one of the things which is depend from one vendor to another, how you can optimize this and that. Then moving forward here, which is the most important thing which we are going to cover next slide, is about something called pre-coding and antenna force mapper in general. This is in general just to try to make it simple for you. This is just like it's kind of the step which is covered the beamforming weights, and this is for sure will depend beamforming weights. For example, whenever the unit B or the antenna or the AS is going to generate the beamforming, right? As we mentioned, beamforming is one of the most important gain in massive MIMO. So it requires the beamforming to be, for example, more narrower, moving in the right direction, left direction, and so on. So this is like it's here. You can say that this is a pre-coding for the MIMO and beamforming to decide the kind of beam weight calculation and this kind of things. And at the end, this is depend again in your configuration because we have different time of beam weight calculation, which can be based on the channel reciprocity, which is sounding reference signal, or based on the codebook, which is, for example, the BMI, and this is kind of things which we are going to cover in next. So this is also one of the very important points which we usually can have a control over it. And this is, by the way, the pre-coding in general is not something standardized by 3GPP. Each vendor can have a different working mechanism. Yes, they are playing around the same logic, but they can have a different implementation mechanism between different vendor and so on. Then after the pre-coding and the antenna or the deciding the pre-coding for the MIMO and the beamforming in general, you will go through something called mapping to the resource blocks and element. So whatever symbols you have it here and those kind of things, you will map it now into a specific resource element and the specific resource blocks where the user will get the information and know where you are going to receive these kind of things. Then you receive, or when he will decode or read the information within a particular resource element or resource block. Then once you have the set of resource blocks, then the afterward this one will have the of the main waveform generation, and this is just it will use this set of resource blocks to generate the CBO of DM or just to generate the waveform in the area interface, as you can see here. So once the user now will start reading and seeing the waveform and start reading and so on, and the user initially this will be generated through the area interface from the Gen B physical layer. You receive it as the UE physical layer. Then it will start doing a reverse like that, what reverse impact or reverse process, which is being done or explained here. Just last point here, as you mentioned, the code word, we have two code words. If you have only one code word, this can generate up to 4 layers. You have two code words that can generate up to 8 layers. So that's it about the data process and streaming. And here I would like to take you a very short sample video about simple analogy video, which is explained in a simplified way about the part on the right here. Yeah, so now let's move to the next slide and see what we have about the features. And as I told you, this is a very theoretical part. You can just skip it in case if you don't really need to understand this kind of information. So let's move forward and see what we have. So the first part we are going to cover here, it's about the first feature of the Massive MIMO. But let me first explain that whatever I'm going to cover today, especially for the single user MIMO, multi-user MIMO, and the channel reciprocity and these kind of things, it will be a high level because the next sessions will be jumping into a very deep details, including the parameters, details, UI capabilities check for all whatever information I'm going to mention, and we'll do deep dive. So first, try to grasp and understand the high level because this will make it easy in the next session whenever you go to the details. So single user MIMO, it's exactly same as whatever we used to have in the 4G, which means that a single user can receive up, for example, to 4 layers or 2 layers or 8 layers. And again, we mentioned that this is dependable or like have a limitation depend of the minimum transmission antenna or receive antenna. Again, we mentioned that example. If you have 2 transmission and 2 receiver, this means you will have only 2, or you have 2 transmission and 4 receiver, this means also you have take the minimum. And again, we are limited usually by the UE side because in the Massive MIMO we have 64 transmission. But if the UE having only 2 or 4, this means you are limited by the 2 or 4. So again, the single user MIMO is exactly the same as the 4G, which means that you have 2 different data streams or 4 different data streams sent from the Gen B to the UE in the downlink, for example. And this is doubling your speed or even making your speed much 4 times more if you have 4 data streams. But what is the advantage compared to whatever you used to have in the 4G? Now we have this kind of a massive MIMO gain, right? And the Massive MIMO gain is mainly again stressing into this point because you have more antennas as mentioned here. This means you have a narrower beams, and this will result in a lower correlation between the beams, and accordingly you will have more irrelevant data streams or less interference between your data streams, which means that you will have a much higher speed and throughput and CNR, which would be resulting in much better user throughput. While in the legacy antenna, the old one, due to the limited number of antenna, which is typically was 4 or 8 or even sometimes 2, because of less beamforming gain, so we'll have, for example, a lot of interference between the beams. Those can result in much less performance compared to the Massive MIMO. So again, it's exactly the same as the 4G, but the main difference is that you can have a good separation now because of the beamforming and number of beams in terms of the 4G, as you can see, for example, in this figure. And yeah, and there's one main question here. I think this is what we're going to cover in details. How does the UNB in general efficiently allocate the multiple beams to different receive antenna? Based on what? Based on feedback, based on watch measurement, and so on. This will be one of the details we are going to cover later on. The second feature, again, it's about MU-MIMO or multi-user MIMO. And again, this is already was being there in the 4G, especially in the TDD or starting from 44R or 88R, which is being represented in transmission mode starting from TM7 and TM8. It was not there in closed loop or open loop MIMO, but it was there from TM7 and TM8 and even TM9. And multi-user MIMO means that, as you can see here, for example, you have 4 users, as you can see. Each one of those users is getting a different beam with the full resource block allocation. As you can see here, for example, in the example in the right figure here, it's assuming there is 2 things, something called UE bird and something called unpaired UEs. So the UE bird, which is considering being as in the multi-user MIMO stage, as you can see, if you zoom in here, this is how the resource will be allocated. First of all, this is the frequency domain, which is like considering as resource block number. So this means if this one, for example, this particular user one, is sharing the resources with 17 and 18, user 17 and 18. And if you look up here for the legend, the 17 and 18 as unpaired. That's why they are sharing the resources. But if you're speaking about user 2, user 3, user 5, up to 16, now they are starting getting the full resource blocks, like for example, complete resource block alone without being shared with any other users because they are allocated in different layer, in different space domain. As you can see, for example, this user taking the beam. So all these 4 users will not be sharing or dividing the resource among each other. No, each one of those will using the full resource blocks or frequency. Accordingly, this will double your speed and even your spectral efficiency. And as you can see in the relation from one of the exercises done before, this is, you can see the spectral efficiency in the white axis and the number of paired layers. So assuming that you have up to 16 layers, for example, and 64T, 64R, as you can see here, that the more the layers per layer, the higher the spectral efficiency. And this is actually one of the is we have now in Massive MIMO, you are improving your spectral efficiency and improving the throughput and capacity without increasing your bandwidth and so on. And one of the important things we would like to highlight that in general, the key to Massive multi-user MIMO is UE pairing, which is actually dependable on 2 things: the radio condition, for example, or many things, but the most factor that all these users must have a very good or acceptable radio condition in terms of CNR, and they should have a good separation between all of them. For example, if they shouldn't be in the same location, because if they are same location, they would interfere each other if they use the multi-user MIMO. And also, this is dependent on the hardware. For example, the type of antenna or AAU you are using, the less number of, for example, 16 transmission only can result in less number of paired users, and so on. And also, unlike the 4G, the 5G supporting now the multi-user MIMO to do all these kind of channel, which is the shared channel and BDCH, while in the 4G was only supporting to that data channel. Now we have also BDCH is being used in the currently in 4G and so on. And this was a very high level introduction about the multi-user MIMO. Now I would like to take you a very good information about the channel reciprocity and differences and how the beam weight calculation is being done at a high level as well before jumping to details. So let's move forward. So in the previous 2 slides, we were speaking about the single user MIMO and the multi-user MIMO, and we'll have an narrower beams and this kind of allocation. So how this all being done? How the GNB can decide where is the user location, what kind of beam he needs, what kind of narrower beams he will be allocated, and so on. So actually, in general, there is something called beam weight calculation. So usually, the GNB should have a particular information, GNB itself, to decide whether this user, which beam is going to be allocated and so on. So what kind of information the GNB require? We have 2 different type of information to have this kind of beam forming calculation to decide either for single user, multi-user. So, for example, you have something called reciprocity-based. Reciprocity-based, which is based on the sounding reference signal. Reciprocity means that for TDD system, as you know, that we are using the same frequency for uplink and downlink, but it's divided over the time. time division duplex. So in this case, we are assuming that whatever radio condition you have in the downlink or uplink will be the same because at the end the same frequency. So we are depending on this case something called sound reference signal. As you know that usually the user is reporting the sound reference signal in the uplink, and the unit B can measure this kind of information to decide what kind of beam or to make the beam calculation and decide what kind of beam will require based on this sounding reference signal estimation. And the reciprocity based in general, this is the green one, this is kind of the gain or the positive sides, and the red one is kind of the negative side, or like you can say limitation, not negative side. For example, SRS, sound reference signal, this is can decide the beam calculation for both single user MIMO and multi-user MIMO. So both we use both of them. First, secondly, it's time measured. For example, it's like based on for sure the time transmission, but it's most of the time it's being there. All the user need to report it most of the time. However, for the CSRS, for example, or the codebook, this is based on the allocation for Journey B and so on. So this is kind of time measured, or in other words, not like that, but in here we are going to highlight in more details next slide. You can see that the user first need to report something called BMI, CRI, and so on to the Unit B before, and Unit B will take the decision. However, in this case, this would be saved because already Unit B directly can measure the SRS. That's why it's called timely measured, that it have the information updated most of the time. Secondly, or third part, it's usually the SRS transmitted over the complete bandwidth. So this means that you will have a higher granularity in case you will have the Unit B will being able to measure the complete frequency, so it will have a much accurate information about the channel condition and so on, so it can give a much better gain. And as you can see here, for example, this particular user, this is based on Reciprocity-Based. The green area here means the good radio condition. So he's reporting sound reference signal, and GNB will decide his beam based on that and start allocating the beam here and so on. And the main limitation that first of all, because again, reciprocity means that downlink and uplink is the same, so it's only used for TDD. For ADD, is using only the codebook. And one of the very important factor, it's having a limited uplink coverage. That whenever the user is outside or very far away or a user, will have a very high risk due to the uplink limitation, because if there, as you know, that usually the uplink coverage is much more less compared to the downlink. So whenever the user is reporting this right in uplink and he's in the edge coverage, this might impact the reporting itself. It will not be accurate reporting because at the end, this is not estimating the actual condition of the downlink, because this is estimating because he's on edge and they have a limited uplink coverage. So this is reflecting that GNB will measure that whatever being reported in the SRS, this reflects also on the downlink, which is not the actual case scenario. And just to summarize that, the quality in general, or the signal quality of the sound signal can easily contaminated by the uplink transmit power shortage at the cell coverage edge. And this is actually because the SRS channel response should be estimated individually at the base station in general, or the base station in general. And when I mention individually, means that, or it can be it doesn't have any protection. Like for example, there is no diversity not applied, there is no any error quantization, or there is no any error correction or detection and so on. No, it's not. It's unlike the BMI code, because for example, when I go to the BMI code or BMI, at the end the user also still need to report this in the uplink channel. So you might ask yourself, this is yes, it's reported in a different channel, which is BUSH. So again, if the user in the edge, should be reflected as well in the bad reporting. But in the BMI, we have or the codebook in general, we have higher. Sorry, excuse me. The BMI is being transmitted under the CSI feedback. I mean, in general, which is standard state information, which is including the information for the codebook. This is usually being transmitted without alteration, and it's received in the uplink in general under protection of the channel coding and diversity gain, which is something not available in the reciprocity gain. That's why it's having limited coverage. But usually the question I was asking myself, yes, it's being reported in the uplink. It's having limited coverage. I understand, because uplink is limited compared to the downlink. But why the same was not being applied to the Codebook-Based, even though the codebook, the feedback should be also reported in the uplink, This is because the BUCH having the mechanism of the error correction detection, while the SRS doesn't have this kind of, it doesn't get this kind of gain compared to the other channels. The second point, actually, or the point number 3 in terms of limitation, this is also required a specific QE capability. This is called something called antenna switching capability, for example, 1T to R or 1T for R. I already explained this in a separate video, but also I will go through the details in the next slide. I will show more explanation about it, how to check it, and what kind of impact we can have in case of you have this kind of limitation. But again, just here it's having or it's have it depend on the UE capability. So not all the UEs supporting this functionality of antenna switching capability, which means not all UEs can use the SRS. So in this case, you'll use the other thing, which is the code book. The last part about here, the one of the limitation as well, it's about the SRS resource availability. Actually, the main idea that, for example, assume that the number of available resources, usually the number of available SRS resources in a cell is usually much less or much smaller than the maximum number of RRC connected users, as we mentioned here, much RRC connected users in the cell. For example, if assume that the number of RRC resources in the system, which can be simultaneously configured to the users, is 128. Then, and each one require a 4. Then, in this case, only 32. If you divide 128 by 4 resources can be converted per users. Only 32 users can be allocated with, assuming that his capability is for R, for example, antenna switching T1 for R4. This means only 32 users can be allocated. So, assuming that you have 100 RRC connected users in the cell and all of them are capable, not all of them can use the SRS because at the end there will be a limitation compared to the existing RRC connected users. So this is one of the things also in terms of channel reciprocity part. But again, this is a much better, giving much better performance if you are speaking about the center cell or in the good coverage nearby to the side. This is a much better performance compared to the codebook, especially for single user and multi-user MIMO. The second type, actually, which is a very detailed one, which is about the codebook-based, or you can say it another word that we usually call the precoding matrix, is having two types. First one called type 1 single or multi-panel, and this is type 1, which is only supported by both FDD and TDD, which is this is compared to the reciprocity-based or TDD. Second part, it's having a higher, much better coverage, as we mentioned during the explanation of SRS. For example, as you can see here, this user at the very edge of the cell. So in this case, it's preferred to use the code book in general, which is a BMI, which is type 1, because it's having more superior coverage. Because again, whenever the user receives the CSRS in the downlink, he will be reporting something called channel state information, CSI, which including a lot of information, BMI, rank indication, CQI, in the uplink, and in the BCH or BUCH usually, but usually it's BUCH. And again, because we mentioned that we have higher quantization and correction in the BCH, and they can get the benefit of the diversity. So we are expecting that even the coverage for this particular and uplink for the reporting would be more accurate compared if the SRS is being used for the edge users. This is the main advantage we have here. It's about the superior coverage in terms of edge users. It's preferred to use the codebook in this particular example. But this is only for the type 1, only supporting for single user MIMO, only for that part. And you can say it doesn't have a UE capability information, but the very old UEs, there is two methods. I will explain this in details later on, but I'll give high level as well in this slide. For example, whenever the user the unit be deliver or unit be deliver the configuration to the UE about the CSRS resources, I also explained this in details before in one video about the CSRS in general. You can configure, for example, based on number of ports, 8 ports, 16 ports, 32 ports, and so on. So usually most of they use the maximum number of ports, which is 32 ports, and not all users supporting the measurement of 32 ports. So some users only supporting maximum as 8 ports. So this is kind of a limitation in case if you are using, but it's in case if they're using 32 port. But at the end, it's not something will impact that part, because if the user not supporting 32, in this case, you will use the 8 port and so on. So I called it partial limitation, but you can consider as no limitation. But it's just about the CSRS reporting capability of the user itself in general. So the 32 usually provide better performance than the 8 ports. We have the type 2 single panel. And this is actually intended mainly for multi-user MIMO because the first one was not for the single-user MIMO, but this has have additional limitation. For example, here in case of multi-user MIMO, it's only supporting maximum of rank 2. So if you are being paired, you can get only maximum rank 2, and this is require a larger overhead because it's going to give you more accurate information compared to type 1. So this require additional overhead, and this is also require kind of UE capability. Not all UE is supporting this kind of type 2. And all these kind of information and details I will be sharing next videos in details, including the UE capability check and these kind of things, to be aware how to check and how to verify this in your network. So now let me give you the last thing here about the, again, high level view about both of them in terms of more visualization to see and understand more about it. But this was, like, you can say, the summary about the advantage and disadvantage of both of them. But just to summarize it, the sound and reference signal is much more beneficial when you're speaking about the center user. It will give you much better performance. Then afterwards, following the type 1, especially for single user MIMO, which is much better in the term of edge coverage. Then the other one, which is multi-user MIMO, or type 2, usually used for multi-user MIMO whenever there is no sound and reference signal. So you can use the type 2 to be having the multi-user MIMO. So this is as a summary for all of that. So let's move forward and see what we have next on last slide. Okay, here again, it's exactly the same, but I'm just trying to visualize it. We'll give more details next videos about these kind of things, about the E capabilities, the exact information. We have a lot of information, especially about the parameters, the configuration for the both of them, especially for the codebook. Also, I will give some ideas about how to optimize both of them in general in your network in next videos and so on. So if you go to the reciprocity-based or the SRS, as you can see, assuming here this is the same user. So the user here at this time 1 is reporting the SRS. So you report the SRS, as you can see down in the signal point of view. Initially, you have, assuming this is user supporting 1T4R, so you can have this antenna switching through using the 4 receiver as a transmitter. So he will using for the 4 antennas, which is having 4 SRS resources being configured from the beginning to this particular user. So you transmit 4 SRS signal, one from each antenna which you have here. So the GNB at that time will start the beamforming weight calculation here, and it will decide the beamformed BDCH, the BDCH beamforming. As you can see, it will be generating that part here. And in case if the user moved, again, he will report the SRS. So in case because he moved his location, so as you can see, the beam itself, it's being changed here. And afterwards, the user will be starting reporting the channel state information, just to report about his current rank indication CQI for optimization and link adaptation in general. So here, as you can see, it's the GNB can directly measure the condition and can directly make the beamforming calculation because the user most of the time reporting the SRS. That's why I mentioned timely based, which is having more accurate information or faster information or more outdated information and so on. And if you're speaking about the code book, for example, I give 2 examples here. For example, the first example here, I'm assuming you have 32 CSI ports being configured. So we are sending a one, as you can see, the beams here for this particular users. And this user will be reading the CSRS from 32 different resource elements or 32 different ports. And I will explain about the ports and the antenna mapping later on also as well. So, for example, here, the GNB first transmitted the CSRS port in the downlink. Then the UE himself start deciding which BMI is best out of this measurement. So to like instruct the GNB to based on the BMI report to tell him, for example, I need this beam at this direction and at X direction and Y, for example, X horizontal or Y elevation and so on. This is actually having a very good detail, very good details. I will be also going through that in next sessions in very deep dive, and it will give you a very clear understanding. But in general, just for the meantime, BMI just telling them which beam I need to get. This is the UE telling them this is my pre-coding matrix, just informing him which beam I would like to get. So you will report something called channel state information, which is including rank indication, CQ, and BMI. And once this is being reported, so now GNB got the information, which is the BMI. It knows which BDCH it requires, so it will do the beamforming directly and so on. there is this here for in case of, for example, assuming that you are using in your network as a configuration 8 ports, or you have some devices not supporting the 32 CSI ports. So this is how it will looks like. The UNIB will be transmitting for CSRS, as you can see here. Each one of those will be using 8 ports, as you can see. So in this case, actually, what you will see in the normal case scenario, you will see for not one, 4 CSRS, each one will having 8 ports on 4 CSRS, which one was 4 ports. Then the user will start selecting out of those 4 which beam he would like to use out of those one. So he will add one additional information to CSI report once he reported back, called as you can see here, called CRI, which is the CSI rank indicator. Like tell him which CSIRS he selected out of those reported here, and also the BMI and so on, which is shows CSI resource indicator, which again which one is the best resource he has been selected, and he will report it back. And in general, 32 is giving better performance than the 8 ports or the 4 CSRS using 8 ports, because as you can see, for example, here, this is reducing the kind of mobility because it's kind of covering a wider area. While here the user move here and there might be changes within his mobility. So, and also this one giving high granularity because the user will measure the condition within 32 CSR ports or 32 resource element, while here it will be only through 8. So the granularity here is much higher, so giving you much accurate information about the CNR and so on. And actually, that's it for the today video. It will covering all, like I can say, a lot of theoretical information and high level information. We still didn't go through the deep dive, but this is very, very important before jumping into the details of even the parameters, how the BMI working, how the codebook being working, the exact differences between different type 1 and type 2, and later on also be covering the uplink, and also what kind of optimization can be done for reciprocity. All these kind of details, you will not understand it if you didn't grasp or understand this kind of high level in a very good details. So that's it for today video. And if you like, please make sure to like and to comment. And I hope you like or comment, because I can see many of you people asking me to one without giving a like or comment to the channel. So if you like it, just press like and share it with your friends and spread the word. Thank you very much, and see you next video.